In this lesson, we will derive the equation for the material derivative. The material derivative is a mathematical relationship that relates the time rate of change of a physical quantity as observed from the Lagrangian viewpoint to the time rate of change of the same physical quantity as observed from the Eulerian viewpoint. Here we have a fluid element labeled A. As discussed in a previous video, the velocity of this fluid element is a function of time in the Lagrangian description since the fluid element's coordinates change in time. However, if we use the Eulerian description, the velocity is a function of time and space. A small amount of time dt passes and the fluid element's velocity changes. The velocity at the location previously occupied by the fluid element also changes. In the limit of dt becoming infinitesimally small, the change in the velocity of the fluid element from the Lagrangian point of view, dVA, is equal to the change in velocity at the location occupied by the fluid element, dV. The full derivative of the velocity from the Eulerian point of view is partial v partial x dx plus partial v partial y dy plus partial v partial z dz plus partial v partial t dt. Now we divide the entire equation by dt. On the right side of the equation, the x dt is the x component of the velocity, lowercase u. dy dt is the y component of the velocity, lowercase v. dz dt is the z component of the velocity, lowercase w. And dt dt is simply 1. Cleaning up the equation, we have a relationship for the time rate of change of the velocity of fluid element A from the Lagrangian point of view on the left, and the time rate of change of the velocity at the same location in space from the Eulerian point of view. Although we derive this relationship for a particular fluid element A, there is nothing unique about this fluid element, and the relationship is valid for any fluid element. So we can drop the A subscript. In the derivation, we started by examining the velocity of a fluid element. However, we would arrive at a similar relationship had we been examining a different quantity such as density, pressure, or temperature. So we can replace the velocity v with a generic quantity alpha. We also can condense the equation by noting that the velocity vector v is lowercase u I hat plus lowercase v j hat plus lowercase w k hat. The del operator is defined as partial x I hat plus partial y j hat plus partial z k hat. So we can rewrite the three terms on the right as the dot product of the velocity vector and del operator, which operates on alpha. Many fluid mechanics textbooks replace lowercase d's with uppercase d's in the time derivative on the left side of the equation to highlight that it refers to a Lagrangian viewpoint. Other names for the material derivative are the total derivative, convective derivative, substantial derivative, and substantive derivative. We will now discuss the physical interpretation of the terms in the material derivative. d alpha dt is the total rate of change of property alpha as observed by a fluid element. This is equal to the rate of change in the alpha field with respect to time at the fluid element's location, plus the rate of change in the alpha field with respect to space at the fluid element's location. Let's examine a situation in which a fluid element will experience a temperature change as it travels over California. In this case, the physical quantity alpha is temperature. The temperature field varies between locations, so partial t partial x, partial t partial y, and partial t partial z terms are non-zero. Additionally, as the fluid element moves, the temperature field is changing in time. So in this situation, the fluid element experiences a change in temperature due to the temperature field varying in both time and space. Now let's imagine a situation where the temperature varies between locations but does not change in time. That is, the temperature field is steady. Once again, the fluid element will experience a change in temperature, but only because the temperature field varies in space. The temperature field does not vary in time, so partial temperature partial T is equal to 0. Let's examine one more situation where the temperature varies in time but is uniform across California. The fluid element experiences a change in temperature due to the temperature field changing in time. However, the temperature field does not vary in space, so the three spatial derivatives are zero. The partial alpha partial t term is often called the unsteady term because it is related to the alpha field varying in time. Steady-state conditions occur when the alpha field is constant in time. The v dot del alpha term is often called the convective term because it is related to the alpha field varying in space.